All right. All right. I think we'll finish up today. There is Friday. I guess I don't even know if the quarter ends on Friday or before Friday, but Friday basically all we need to do is you don't need there. There won't be a video. I don't believe I'll make a video on Friday. Really, the main thing is uploading all your assignments. If you are graduating in the summer, I don't think any of you are, but if you are, then I need to know that because I need to get your grades in earlier than anyone else's. I haven't gotten an email or anything indicating that there are any graduates for the summer in this course, but if there are, let me know because that does change when your grade needs to be done. Quiz 3, this one, it says course assessment quiz, which that's what it is, but it actually does count as a grade, so it is the third quiz. It's 5 or 6 questions that are free response, so there's no way to get it wrong, but you do have to fill it out. I guess there is a way to get it wrong, just don't do it. But fill this out, and it doesn't take very long to do. You can put as much time into thinking about the questions as you want, but I just need, I don't even need, I just want some responses here. It's, things that could be done differently in the course or reinforced or removed or whatever. So do that as quiz 3. It says it's due August 13th, but if you are planning on graduating this summer, I need it very soon so that I can get your grades done. Today, what I thought we would do is go over to Solidworks and look at the primary pieces of an extruder, do a little simulation, a thermal simulation. I like using the simulations and things like that just as a visualizing tool. I don't know that we'll get exactly the right boundary conditions on this thing, but we'll get close enough that the results make sense. And I'm using here's the model. Where'd it go? Well, only the nozzle is visible right now, so I'm using nozzle. I'm not modeling threads. You can see I've made every part that's a thread just a cylinder to represent the contact. I'm not particularly interested in the actual thread to thread interface and all that sort of thing. We can even model that without the geometry. We can model that with coefficients in SolidWorks if we really, really wanted to do that. But I used E3d V6. Let's see. What I want to look for. They actually have E3d. Yeah, here we go. They actually have all of the drawing files, the CAD files for the E3d V6 nozzle. It's open source, so if you have a lathe, most of these parts are made on a lathe anyway, except for the heat block. You could go make your own. That's why you see so many knockoffs of the E3d V6, because here's the blends right here, and you can make your own or tweak it somehow. So I use these to get the actual dimensions, and you'll see in theirs even they are modeling them, or at least they're showing the picture without. Oh well, that's not the one we need to go to apparently. But they have them. They do have them out there posted. That particular one that I picked was not available apparently. Let's see. This one looks like it probably is. There we go. This is on the actual E3d website, and so they have all of these, and they're indicating the thread. I don't know if you can see that or not. M6 by 1. You can see right there. This is not for the V6, I don't believe. I don't see exactly. Well, yeah, it is E3d V6. It is for V6. All right. So you could actually create your own based on the actual plans from E3d. They have the heater block, the nozzle, the heat sink, the heat break. They're all here. They have some exploded views, some cross-sectional views, so you can make your own. So that's what I did. I grabbed, I think I did an all-metal version. Once we get back over here, we'll see. And let's see, where's the heat break? That'll tell us if it's all metal or not. So, well, there's the heat break. You can kind of see what's going on with the heat break. So I don't have the heat block where the heater itself is. I don't have that shown right now, but let's do a cross section. Let's see if we can find the center. There we go. There's the center. So yeah, this would be an all metal version. So the difference would be probably, unless you have an upgrade or maybe a non-standard E3, not E3d, Ender 3, you would have the ability to take this nozzle off, remove the nozzle, leave the heat break in place, leave the heater block in place and everything, and the Bowden tube would be able to shove all the way through here and come out the bottom of the heat block. In fact, that's a decent way of removing clogs. Let's say you get a clog that you just can't get out of the Ender 3 style hot end. Take the nozzle off, shove the Bowden tube all the way through the thing, and it will purge everything out of there. At that point, you could even resurface the end of the Bowden tube. I have. Let me show you what I use. Let's see. I'll have to find one. I use this little guy. So it's you can print these too, and just put a utility blade knife in there or something like that. But if you buy a Capricorn tubing set, most of the time they come with these. So you end up with a bunch of these if you buy a bunch of tubing. But this is, it's just a little guillotine type cutter that helps ensure that the tubing, the Bowden tube, is square on the end of it. And like I said, you can print these all day long on Thingiverse. They have plenty of tubing cutters that will do a similar thing. You want a really sharp blade because you don't want to squish the Bowden tube, and you want it to be square because on a printer like that, and on this printer too, but this one I'll show you in a second why it's not as important, but it still is important. But that larger area where the Bowden tube rests ends up way down here where the heat is still potentially hot enough to liquefy your filament. And if there's a tiny little gap, the end of your Bowden tube is not square with the top of the nozzle, then softened filament is going to leak out the side of that gap, and then and harden, or at least solidify to the point that it's not easy to extrude anymore, and that's going to cause under extrusion, and because not as much filament is going to be coming out of the nozzle, it's going to kind of hang on that bulge, and it will eventually probably cause a clog. All that to say, the whole point of that was all metal versus not all metal hot heat break. So this is an all metal heat break where you can see the Bowden tube actually can't go past here. This little surface right here is where the Bowden tube is going to sit. At this point, the heat is down here. The heat block, let's turn it on. The heat block, the heater's in this hole, and the heat block is, down in this region somewhere. There's a very thin area, can't really highlight it, but across here, or cross section, I guess I could do a cross section that direction, but there's a very thin area of conduction, but it doesn't have a lot of thermal mass. There's not a lot of mass in this neck of the heat break. There's a little bit of radiation. You're going to have, this block is 200 degrees basically, and there's going to be a little bit of radiation there, but surrounding all of this is our heat sink, this big giant, compared to every other part here, aluminum heat sink with a fan blowing across it. So it is conducting heat away as fast as it can. You have convective cooling on these fins because there's air blowing across it. That's the fan that's always on, is blowing air across this thing. All these surfaces. When I model, or when I do the simulation, I'm just going to use the flat surfaces, although technically it would be these surfaces also, but It's not worth me going around and trying to click all of those. I just use the flat surfaces in the model. And so you can kind of see where the Bowden tube ends right here in this kind of nozzle. And so some people get confused. Well, that's not all metal. The Bowden tube goes down in there. That's true, but the Bowden tube ends at a point where the heat at that point should be below the glass transition temperature of your filament. The reasons it might not be are, number one, the fan blowing across these fins has quit working. Maybe you took it all apart and you put it back together, but you put the fan backwards. Typically this fan needs the label, so it's a little sticker on the fan. It needs it pointing towards the heat sink. That's usually indicating the area that the air is going to be pushed. Bigger fans will have actual arrows on them showing which way the fan is rotating and which way it is pushing air, but these little ones usually don't have that on there molded into the case of the fan. But typically the sticker is kind of telling you which way the air is going to be forced. So you have forced convection across the surfaces here. You've got a lot of very conductive, thermally conductive material, and this is almost always aluminum for the heat sink, sucking heat away from here. And so at this point, you really shouldn't have a softened filament. It should be pretty much its regular state. Another reason that this can go wrong is you take all this apart and reassemble things, and it is possible to put the heat block back together in an order where this surface is actually touching this surface. And so then not only do you have well, I guess you still have some radiation a little bit from the heat block radiating heat, so like through the air up here, but you have direct conduction when you push this surface against this surface, and that amount of conduction can be enough to even on a all metal hot end can be enough to get heat sufficient in this zone to melt or at least soften your filament, and that can lead to clogs and under extrusion and all sorts of problems. So when you're reassembling these things, normally you put the heat break into the heat sink, then the nozzle pretty much all the way into the heat break, you know, maybe a half turn less than snug, you know, something in that range. So it's pretty much all the way screwed in. Then you attach all this stuff together, and you don't have to have the heat break in the heat sink to begin with. That can be the last step if you want it. It doesn't really matter. It might make it easier to screw everything together. It depends on if you've got this out in front of you or if it's attached to the printer, right? If it's attached to the printer, then it's probably going to be difficult either way. So, because you have to screw these things together. Some of these heat breaks are not a press fit. They're a loose fit that are held in with maybe a grub screw or something like that. But a lot of them have threads in this region up here that screw it together. And again, I just modeled that as a cylinder. So what you would do is put the nozzle almost all the way in, attach the heat break to, the heat break to the heater block, and then heat everything up. So at that point you do have to have it attached to the heat printer, at least so that there's heat being able to be delivered to it, which means you have to have the thermistor. This is the thermistor hole, and this is the heater hole. You'd have to have both of those filled with the thermistor and heater. And then tighten the nozzle the last, you know, half turn or 3/4 turn, whatever is left, and you should have a gap between this surface and this surface so that you don't have direct conduction. And that usually is accomplished by, you know, this interface right here. All right, so what I did is I built all these parts based on the E3d drawings. And then I ran a thermal simulation. Let's just do a new study, and I'll start it from the beginning. it doesn't take very long to set it up or to run it, the one I'm going to do. And that'll kind of walk us through the different things that you might have to add. So I'm doing a thermal study. I did not use 2D simplification. That would probably be okay, but I didn't use it. It's not quite. This is a line of symmetry here, so I could do a half model if I wanted to. Couldn't really do a quarter model because of the way the heater cartridge is not symmetric left to right if I'm in this orientation anyway. So I'm going to have to add. My favorite materials don't include the materials that this thing is made of, so let's add a material, which means I've got to open up the material interface, which is usually pretty slow when I'm streaming stuff. Hopefully it'll come up pretty soon. Looks like it's working on it. So I clicked the heat break. So the heat break a lot of times is a stainless steel. Let's use that's a sheet. Let's just use a 321. I don't know what exact alloy it is, but let's use a 321 stainless steel. You can get titanium. I don't know if Solidworks can model titanium. I assume it can. Yeah, there's titanium. Let's put a titanium heat break in there. The reason you might want a titanium one of the reasons anyway, is that this titanium is incredibly strong, and that can give you a thinner wall right here so that you have even less amount of conduction possible, assuming you put it together right. And so you can have an even thinner wall right here. So sometimes you don't find that by default, but you can order a titanium heat break. Let's look and see what sort of price. I don't know if they have on Amazon, but it seems to have everything else. Titanium heat break. Let's see. Well, it's got a horrible review, but only one rating, so I don't know. But it looks like maybe in the $15, $20 range. This one's coated with copper to have a little bit better conduction ability in the heat sink area. Here's a heat break for $30, so looks like they range in price. $15 being kind of the average, up to, I'm sure, much more than that, depending on if it's all metal or if it's not all metal. So you could add one of those. You would have to have a good reason to add one, because other than the fact that it gives you a really thin gap right here, it doesn't do a lot other than that. It has a different heat capacity, different heat conduction coefficient, so it is different. It is a different material, but you would have to have a need for printing at extremely high temperatures for it to make sense. Now, if you shear one off sometime, you know, the steel one, you shear it off and you need a new one, then yeah, maybe $15 or something. It's worth putting a new one in there, and that might make sense. I don't know if I would intentionally just replace a good heat break with one just because I wanted to, but because unless you're printing at really high temperatures, it probably doesn't make a lot of sense to do that. So let's see. The heat sink pretty much is always aluminum. I don't think I have an aluminum in here. Let's put a 6061 aluminum. Again, I don't know the exact material that it uses, but that's a pretty common one, and I'm going to assume that that's what they have there. So that's the heat sink. Heat break is the little cylinder here. The heater block, a lot of times that's also aluminum. You can also get these that are coated in copper for better heat conduction reasons. But I'm going to make this one kind of just aluminum. Same 6061. The nozzle I'm going to make as, I think I do have a brass in here. There's a brass. So by default, most nozzles are brass, but you can obviously get the hardened steel and different materials. You can get some that even the whole nozzle is not, but the orifice here is ruby actually. So you can get all sorts of different types of nozzles. Brass is the default nozzle. So there's our materials. Again, I'm just doing the cross-section view here. It is a whole model, but helps us see what's going on if we look at the cross-section. All right, so components contact. I'm going to do a contact set. So I'm going to automatically let it find the contact sets of touching faces on these components. There's the 4 main pieces here, and find contact sets. So it found all the this is touching that set of relationships. And here we have a couple of options of let's see, thermal resistance. So thermal resistance, what this is trying to model is even perfectly made parts. So you take and perfectly made I mean by human standard, so they're not actually perfect, they are within some tolerance. Even those are not going to have full 100% contact between the surfaces. There's going to be air gaps. In Solidworks, when you look at the thermal resistance, let's see, I had it pulled up. There it is. Thermal contact resistance in their help section. You know, they give you this diagram here, kind of showing it looks like parts A and B are, you know, perfectly in contact, but in reality there are little gaps between these two surfaces because of manufacturing level imperfections in the surface of those parts that were made. So one was drilled, in our case, you know, one was drilled and one was turned on a lathe, and those are supposed to fit perfectly, but in reality there's these little air gaps. And so there is conduction between them, but really the conduction is happening only at the points that are in contact, and these air gaps can't conduct. They have to use a different method for getting the heat across there. And so this thermal resistance is measured in these conductance or these thermal resistance values. Let's see what units it's asking for in Solidworks. I didn't notice. Kelvin per watt. So these are kilonewton. Well, that's contact pressure. These are watts per meter cube Kelvin for conductance. So they don't give you an actual value here. You'd have to go look that value up. But there's different contact sets between different materials and different values of this conductance between there. Let's see if we click on their example, if they give a typical value, or if you know, something that you would need to calculate. I don't actually see a value in here. Yeah, so it's something that you would need to go in and calculate. So I do have it checked, but I just have it set at 0 Kelvin per watt. I don't know what's in the advanced tab. Let's see what's down there. Oh, okay. Yeah, this is talking about how in the mesh, how is it going to work. And the default is a node on the mesh to the surface it's contacting. And so node to node, I imagine, would probably be faster simulation wise, and surface to surface would probably be slower simulation wise, but the node to surface in this model didn't take very long to do. So the other thing that we could choose if we don't check thermal resistance is that it's bonded, so it just does assume that it is in perfect contact. So since I don't know a great number to put here, I'm essentially creating it like it's bonded because I put 0 in here. Any other number in here would simulate this fact that there is some gaps between our surfaces, that they're not perfectly made. And so the worse manufacturing quality you have, the more thermal resistance you will probably have. All right, so I'm going to leave that the way it is with just 0 for now and get that as a first approximation. And we do want to create the contact sets. All right. Thermal loads. So we need to add some kind of heat going into this thing. So since the way this works is I've got the heater in this hole and the thermistor in this hole. And so it is a closed loop feedback system where I'm constantly, well, assuming everything's working correctly, I'm constantly measuring the heat, and the heat is on one side here. So I'm measuring the heat on this side, and I am applying the heat on the other side. And so if anything gets out of whack, then I either apply more heat through the heater, or I apply less heat through the heater. So I increase or decrease the amount of heat coming out of the heater based on what the thermistor is reading and whatever algorithm and tuning that I have set up. So this is where the PID tuning comes in. Remember, we usually do that early on. It's not necessary. Usually printers ship with close enough PID tuning, but once you get the printer set up in its printing environment, it's probably a good idea to go ahead and do the PID tuning if you have a way to interface with your printer. Usually you do have to get a USB connection to the printer to send it the right, I think it's 503 is the G code for that. Maybe it's 303, I don't remember. Have to look that up. But to tune that proportional, integral, and derivative control of the relationship between what the thermistor is measuring and what the heater is doing. And so I just chose to apply a temperature, assuming that my system is working fine, and it just keeps a 200 degrees Celsius temperature at the surface here. Technically we want that'll be over here, is where the 200 degree temperature is. So this is probably a little bit higher than that, but not significantly higher. So that's what I did. There are others. You can put a heat power or heat flux in here and do more of a transient type analysis. So maybe you want to know how long does it take to heat up or something along those lines. Then you could do one of these, but I'm just going to treat it like a closed loop system and set that to 200 or whatever you want. Maybe you want to see if your setup will work with printing some of the hotter temperatures. So you need to be at 250. Then you can kind of check, whoops, scrolled the mouse wheel and it messed it up. You could check and see if you were going to have issues with heat creep into your cold side of your hot end. So I just applied a temperature there. So that's simulating the control system working. Let's run it this way first. So what I don't have right now is I don't have any cooling. So there's no convection across these surfaces right now. So it's just 200 degrees at this, and I should have had an option for ambient temperature. Let me see if I can find that. Not in there. Maybe it's in the thermal load. No. Well, I didn't get a place to put an ambient temperature. That probably would affect it. I assume, and I don't know this, I assume that Solidworks just assumes the surrounding air is more or less like 23 or 4 whatever degrees Celsius. But let's mesh and run this and see what we get. All right, so wow, I get ridiculously high numbers here. Oh, but that's in Kelvin. But still, that's going to be a little bit high. Let's no, that's 200. But it shows a gradient, but they're all the same number. Let's see if we can see a cross section of this thing. Section clipping. Well, it's going to show it on that side. That's fine. And let's find there we go. So it looks great, except that our chart is telling us that every color is 200 degrees. And the way this simulation is working, it's not a transient analysis, so it's assuming some kind of final steady state. And that probably would be true if you didn't, eventually, if you did not have a fan cooling the heat sink, then eventually it will reach some steady state where it too becomes 200 degrees Fahrenheit. or Celsius, more than that Fahrenheit. So that would eventually happen. But the thing is, it doesn't even have to get to 200. As soon as you get to, depending on the material, 70 degrees Celsius, maybe 80 degrees Celsius for some materials in this zone, then it has softened the filament to the point that it is not able to be pushed out of the nozzle. So it doesn't have to get anywhere near this bad. Let's add our convection. So that's going to be, I think, is that in the thermal loads? Yes, there's a convection. Let's add our convection. So this is the fan blowing across these surfaces. So let's see if we can select these. And then, oops, didn't get that bottom one. Then let's do the bottom sides too. And again, like I said, I'm not going to worry with the edges. They do, have convection on them, but I'm not too worried with it. Now, all right, so those are the surfaces I'm going to account for the fan blowing across. This has a convection coefficient, watts per meter squared Kelvin. And it's set to 0, so if I keep it at 0, that's essentially, it's not, the fan is off. What number to put in here is tough. So just open air, if there was no forced convection like we have here with the fan blowing, then maybe 5 watts, somewhere in that range. The problem is once you do the forced convection, then this number ranges from like 20 to 300. So what exact number to pick, you would have to go in and do some more analysis to figure out, all right, what kind of fan do I have? How much air is it pushing across there? What's the temperature and all that? Here's the ambient temperature right here. Well, let's not do 273. Let's do, I don't know, 290 Kelvin maybe? I don't get the choice to put it in different units. So let's use the lower end of our range, 20 to 300. So this is going to be the lower end of our forced convection variable that we could put in here. It's probably higher than this, but I don't know what the number to put in there. So I'm going to use the most conservative number that exists in the range of typical forced air convection. Liquids, if this was liquid cooled, then this number is suddenly like 20,000 or some, even greater number than that. But 20 for open air forced convection is kind of at the low end, or it is the low end. So I'm going to do that. Because this is a tiny little fan on these things, it's, it's probably at the low end. So let's rerun this study with convection. It's going to look the same, but hopefully over here our numbers are much, oh, there we go. So it's fine, but it bugs me. I want it to display as just not scientific notation for this particular number. I assume I can do that. Maybe I can't. Oh, there we go. I just want a floating point number. There we go. So 57. Now, it's still, kind of hard. Right here, there's a little bit of that heat creeping in there in the cyan color. So that, that could be even up at the 100 range, 90 to 100 Celsius. And in some of your printers, this zone in a not all metal hot end has the Bowden tube right here. Well, actually it goes down further. It goes down to right here. Basically it sits against the nozzle. And so that could be a problem if you have that kind of temperature inside the Bowden tube. In fact, this one would give us a lot of problem because the Bowden tube, well, not a lot of problem, but the tubing material that most of these are made from has a breakdown temperature 250 Celsius. So if you were trying to run this, look, the pretty much the entire heat block end is at my 200. So if I put 250 here, probably most of it's at 250. And so that's why The all metal hot end, where you have the all metal heat break, is needed if you want to print some of the nylon for sure. Print a long time with ABS or PETG that need to print at the higher temperatures. PLA is not going to be a problem, and ASA is probably not going to be a problem. PETG is not necessarily a problem, unless for some reason you're having to print it extra hot. But it can print at a lower temperature than what would be the breakdown point of the Bowden tube material. But now we're at 60 degrees, which for PLA, 60 degrees Celsius does start to get close to its glass transition temperature. I think it is 65 or something like that, and it probably depends on the blend of PLA, but it is in that range. Now, in this setting again, all metal hot end doesn't mean anything other than the heat break itself doesn't let any kind of plastic material get down to the really hot part. And so the plastic material, the cooling up here is, it actually still is about 60. It looks like all of this is about 60 degrees until we get down into this region down here. That is with our lowest estimate for the convection coefficient being 20. I assume it's actually higher than that, but I didn't go measure that or anything like that. But this is kind of how the hot end works. They have different arrangements of heat sinks, different materials possibly, but this is a typical arrangement for a 3D printer, FDM 3D printer hot end system, and this is more or less how they work. You have different combinations where this heater on a volcano, for instance, a volcano hot end. This heater is aligned vertically with the nozzle to try and get more heat right up against the nozzle. And so obviously that makes the heat break longer. So you lose a little bit of Z printing height by using a volcano hot end, but you gain more heat being put into the filament right beside it, vertically beside it, aligned with it. And so you usually want to do that if you're trying to print with a really large nozzle or print really fast. The faster printing speeds mean you have to extrude more filament. And so in order to do that, you have to melt it faster. And so, the faster you want to go, the larger nozzle you want to use. Basically, the more volumetric flow rate you need of filament coming out of the nozzle, the more heat you're going to need to be able to get it to the point to where it can actually be pushed out of the nozzle. And so there are different arrangements of heaters, and some have 2 heaters. And so there's different arrangements to accomplish that. But your typical printer is more or less these 4 parts. A heat sink to get the heat away from the filament before it's ready to be melted. A heat break to isolate the hot end or the hot side from the cold side of your extruder. A heat block to contain the heat and direct it into the nozzle. And those 4 pieces make up pretty much all the iterations of FDM style hot ends. There are different shapes and different materials, even different coatings, and different arrangements of stuff, but that's generally how they all work. There's some really experimental fancy ones where they use a laser to preheat the material, and so they can heat it super fast, and then let the cartridge heater to do the final heat. So there's other things out there that are, I don't even know if you would find on a printer you could buy, but there are experimental ways to do this also. But I don't know of any commercial thing other than something like this. So hopefully that gives you the last little bit. I mean, we've talked about this stuff before, but maybe this, what I'm thinking is most of the time when you have printer troubles, it's a clog of some sort. And so maybe this little bit of knowledge will help you figure out how to get rid of the clog, or remind you that, oh yeah, maybe the Bowden tube is not pushed in all the way and there's a gap between it and the nozzle, or something along those lines. To usually when you're experiencing under extrude, when it's coming out of nowhere, maybe the first time you set it up there could be other problems, but when it's coming out of nowhere, you've been printing fine and then suddenly things aren't working the same, usually it's something with one of these pieces. Over time, the brass nozzle itself is going to wear, even if you only print PLA. But if you print anything that's abrasive, glow in the dark, or the wood feel, or certainly any of the metal feel filaments, anything that has any amount of abrasion to it is going to wear out a brass nozzle before the filament roll is done for sure, and probably way before that on some of these filaments. So at some point you will need to replace the nozzle, and there's a risk there of at least two things happening. The first thing is you just go and you unscrew the nozzle without heating it up, and the risk there is that it has seized in the aluminum block and you end up shearing the nozzle off, or you shear off this little neck right here on the heat break. So there's always a possibility of one of those kind of things happening, and then you've got an entire replacement job to do. The other possibility is that you get too close when you reassemble. You get too close between the heat block and the heat sink. So you get those too close to each other, and they conduct heat instead of just radiate heat between each other. And so that can be a problem, and then cause you more clogs. So understanding the way this works will probably help you troubleshoot most of the printer problems. You're going to have other problems from time to time too. Other things are going to wear out. Don't forget that over time the belts are going to loosen. Things like that are going to not always stay perfectly fine. So some of the things that I do on these tiles, Ender 3 style printers, is I put little white, I use this guy, where'd it go? Use this. Oh my, can't see that because my camera froze up. See if I can reset my camera. There we go. I use this. It doesn't matter if it's this or not, but I use something that can mark on the wheels, and I put a little white mark on them, and particularly the ones on the gantry that are moving up and down, you can see that they're turning, and they're all 6 turning. If you see that they're not all 6 turning, then you might check and see if something's come loose, or you've got somewhere. You should be able to get all 6 of those wheels turning. Now there are some printers that have 4 wheels on the side, and it is possible or even hard to get all 4 of them turning, because it really only takes 3 points of contact to lock it in place, and that 4th one's just kind of the extra wheel. I've heard of the 3rd wheel before, but the 3rd wheel is actually necessary. It's the 4th wheel that's the problem. So I use something like that to mark on it. I don't know if the camera was off or frozen rather when I was talking about this. This is the little cutter that I was talking about with the Bowden tube. And again, that's the thing I said, that you can print those pretty easily, or you can cut them other ways. Just be sure you're using a sharp so you don't squish the end of the Bowden tube, and make sure that you're getting as square as you possibly can, so that there's not a gap between it and the surface that it's sitting on inside of the hot end. So hopefully that will give you enough little hints of what to check when things stop working. I do keep the Discord channel running, so if you stay in there, you can always come back, assuming it's still running, and ask for a question about what might be going on with your printer, and either me or somebody else in there can usually give you a hint on what to look for to see what's going on. All right, so I think we'll end there. I probably won't post any more videos. I know I won't post any more for the course. I don't know when I'll post more 3D printing videos. I teach this class again in the winter, so I will post some then. Although I assume that will be in person. Who knows? But I assume it'll be in person. But I still usually post some sort of videos because there's going to be new things, and sometimes it's easier to see them on a screen versus trying to look at what I'm showing and you're 30 feet away or whatever. You just can't see it as well. So, and I'll post some occasionally. Actually, the next class that I teach, and it probably is in person too, but I don't know that for certain. But the next class is actually a measurements course, so it actually does have some overlap with 3D printing, the control side of 3D printing, but that'll be in the fall. I don't know when I'll put another video out about 3D printing or not. I have some ideas of some that I kind of want to do on the side, not really part of a class, but I kind of want to do that Voron build, or at least bits and pieces of it as I get it done. And so there'll be little updates, but not anything quite like the regularity of what these have been. But we'll see what all comes out. All right. I will see y'all. Don't forget to finish out the quiz 3 and then upload whatever assignments you have left to upload, and let me know. Send me an email or a Discord chat that if you're graduating this summer, so that I can know to get your grades done early. Otherwise, it's been a fun class. I liked it. It's not quite the same as being in person, so I do appreciate the people that interact a little bit, so it makes it feel a little less like I'm just talking to a screen. But we will be back with some new stuff shortly. But hopefully the class got you some interest in additive fabrication, and now it's giving you a taken off point for something. Also, be sure, for those of y'all actually taking the course, be sure to put it on your resume that you have a course in additive. You can call it whatever you want: additive manufacturing, additive fabrication, 3D printing, or whatever. That's a really great thing, conversation starter type thing in a lot of industries, particularly that engineers typically go into. It's at least a interesting thing that industry is interested in, and they don't necessarily all know what to do with it. And so having that on there can get you an extra little conversation piece that isn't always available to everybody. Oh, thank you for the comment. I think I like this class. It's a fun class. It's a little bit scattered, because this is a big topic, and so we try to center things on FDM, but there are a lot of different styles of printing out there, and so and some of it that I can't even show you because it's too expensive. Some of these printers are ridiculously cost for the selective laser melting printers and things like that. Someday though, maybe we'll get one of those to show off. Anyway, I will see y'all later. See you in the Discord. Answer any questions you have, and it's been a fun summer. See y'all.